61A, lecture number 37, Q&A. I hope you're ready for some exam problem practice. We are going to take a look at the spring 2018 final, question number 5, which has one of these functions where you call it a bunch of times. And here in this case, it looks like you decide how many times you're going to call it, and then you call it that many times, and then you get a number. So for n greater than 1, an order n function takes one argument and returns an order n minus 1 function. Except there would go forever, except an order 1 function is any function that takes one argument. Okay, so eventually you get to something that doesn't necessarily return a function, but could return anything. Okay, implement scurry, which takes a function f and a positive integer n. F must be a function that takes a list of arguments as its argument. So it takes one argument, which is a list. And scurry returns an order n function that, when called successively n times on a sequence of values, returns the result of calling f on a list containing those values. Okay, so it's kind of like curry 2, where we turned a 2-argument function into a 1-argument order 2 function. But here we have to do it n times, and it looks like the way we're going to do it is with a helper function, where we pass in some k and something called args so far. And if k equals 0, seems like that's when we know there's no work left to do, then we're going to kind of return the final result is what I think is going on here. Otherwise, we have to accumulate more arguments. So for this question, I think I would start here at the moment that we actually do the work. We've got a function inside of a function. We could refer to f, n, k, and arg so far. Seems like k is some counter, arg so far. Well, when k gets down to 0, then maybe arg so far has all the arguments, and it's time to return the result of calling f on args so far. That would actually call sum on a list containing 1, 1, 3, and 2. Now we have to build up that list of 1, 1, 3, and 2 incrementally. So let's see how we do that. If we already had a list of 1, 1, and 3, then we would want to recursively call h on k minus 1 and one other element. So that would be arg so far plus, and here I'm going to use list addition in order to build a slightly longer list. But kind of the interesting part is what goes in here. Well, we don't really have a name anywhere for the next element that we're putting in. And so I'm going to call it x. But in order for x to be bound, we need to have it as an argument to some function. We don't have that function anywhere yet. And here, I think you have to think about all the different ways that you can define functions on the fly. It doesn't seem like anything here in the skeleton code provides this function which takes a new argument and puts it in the list. So we're going to have to write a lambda to do that. Okay, so what this says is if there's more than 0 left to accumulate, then I need to build a function that takes one argument. So something like this function takes one argument. And what does it do? Well, it uses that argument to add into the list of args so far, and then recursively calls on h with a smaller k. Now k would be 0 and would actually call sum on 1, 1, 3, 2. Yeah, that looks pretty good. So now we have to get this going. The first time you scurry, you build a function that needs n arguments and has none of them filled in so far. So this would return a function of one argument that is going to take n minus 1 more arguments later after it adds in the empty list and the first argument in order to get things going.
You started off the question by saying you couldn't figure out how to deal with variable number of parameters. That's the magic of that lambda expression.
Yeah, I think that's a good description. So do you ever need to build a function that takes an unknown number of arguments or not? I guess the way we determine that is to look at the example and see like, okay, all the calls to scurry always take 2 arguments, and all the subsequent calls always take 1 argument. And we're doing it a bunch of times, but we're never have like more than 1 argument within any set of parentheses. So that is the reason that we never really need like an expression for defining a function that takes an arbitrary number of arguments. If you did need that, there is syntax for it. We did see it briefly in Project 1. I don't think I've ever seen it on an exam, but is that star args notation that you saw long ago.
Yeah. A lot of programming languages have the ability to pass a variable number of parameters to functions. Like Python does it. You can have optional parameters. I think Java has it also, where you don't necessarily know what's coming in. The other way to do it is you just bundle up all the. If you're writing your own code, you just bundle everything up into a little data structure, and then don't worry about it, right? That's the easier way to do it.
Okay, so now we're moving on to 5B. Same exam, spring 2018 final. Implement factorize, which takes 2 integers n and k, both larger than 1, and returns the number of ways that n can be expressed as a product of non-decreasing integers greater than or equal to k. Whew, okay. So we factorize n. We have some starting value. If we factorize 7 using parts bigger than 1, then there's only one way to do it, which is 7. If we factorize 12 using parts bigger than 1, then there's 4 ways to do it. 2, 2, 3, 2, 6, 3, 4, 12. So just going through all the parts of this definition, the non-decreasing integers part is so that we don't get repeats. We don't have 3, 2, 3 and, or sorry, 3, 2, 2 and 2, 2, 3. You only get one version of that. And none of these examples show a k that's different than 2, but you could imagine one. So if you passed in 12 and 3, then 2, 2, 3 wouldn't be allowed, and 2, 6 wouldn't be allowed. There would only be 2 ways to factorize it, and it would return 2. So let's just make a note of that as we go. That if instead we called factorize on 12 and 3, then we would expect to get 2 as the result, which is 3 times 4 and 12. Okay, and there's like lots of ways to multiply integers together to get 36 apparently. So this looks a lot like competitions, except for that we have a couple of differences. One is that we're multiplying instead of summing, and the other is that we don't have some maximum part size, but some minimum part size, so we'll have to work our way up. Now, how would we know what to work our way up to? Well, parts bigger than n wouldn't really be useful. You never have a way of multiplying to 12 using 13 if you're multiplying together integers. So it seems like we'll hit a maximum there somehow. All right. When do you know that there's only one way to do it? Well, I would say if you're coming up with ways of factorizing, there's a couple possibilities we could put in here. I think if you've got 0, that's probably one. There's maybe another case, which I'm not sure we need to write down explicitly, but I'll just make a note of it now and we can work out the details later. Maybe it's the case that if you're factorizing n using parts greater than or equal to k, and these two are equal. So you're factorizing 4 using 4 or larger, well, there's going to be only one way to do it, which is that you have that 4. So I'll just stick an or in here for now. Maybe we don't actually need both of these, but they certainly don't hurt. Okay. When is it impossible? Well, certainly one case where it's impossible would be if k is bigger than n. Then there's no ways to do it. And why did I say impossible instead of 0? Well, we have to remember what we're doing is counting the number of ways to do something. And so if there's 0 ways to do something, that means it's impossible to do it. Are there other cases? Well, I think we should get the recursive call set up, and then we'll decide. Okay. So, it really matters that sometimes you can evenly divide k into n, and sometimes you can't. So here we need to look at how we're going to split up all the possibilities. I think you can split up all the possibilities by having those that include k, 2, and those that don't include k, 2. So in order to get the ones that don't include k equals 2, we would factorize the same n using k plus 1. That describes all of the ones that don't include the smallest k allowed. So if we just write that down, at some point we're going to factorize n using parts that are at least k plus 1. When is that the whole answer? Well, I think that's the whole answer when k doesn't evenly divide into 12. So if it turned out that there weren't any with 2's in it, then the whole answer would be just the ones with 3 or bigger. So if n% k does not equal to 0. Otherwise, there are some that include 2, and there are some that don't include 2, so we should probably add those together. Factorize n k plus 1 is the ones that don't include 2. How do you get the ones that do include 2? Well, I think you would divide out k into n. So what I'm looking at here is that this makes 12 because this is a 2 and this makes 6. This makes 12 because this is a 2, that's k, and this makes 6. So if we wanted to look at all the different ways of making 6 using parts of 2 or larger, we would write that in general as factorize n divided by k, k. There's some chance we're done, but it's probably worth looking at some examples to make sure that we have the right base cases. So what would happen with this 12-2 example? We'd hit this case, because k does evenly divide into n. We'd hope that this gives us 2, the first 2. We'd hope that this gives us the second 2. And how would it do it? Well, for example, we'd make the recursive call factorize 12-3, which would then have to make both recursive calls. This one would be factorize 4-3. And it turns out there's only one way to get factorize 4-3, which is to factorize 4-4, and we'll hit this base case and return 1. Oh, that looks pretty good. I think this is not really needed.
Yeah, I don't know why. We don't care about n being 0, right?
Yeah, we're just dividing. The only way n gets smaller is by dividing by an integer. It never really gets to 0.
I suppose if k equals 0, I don't know. Oh, no, we said it's strictly positive, yeah?
Yeah.
Both larger than 1, yeah, okay.
You might get exactly the same result if you wrote n equals 1. Because imagine n were k, then you'd go to this case. This one would turn out to 0 because you'd hit that base case. And this one would divide n by k, they're equal, so you'd get 1, and you'd reach this base case. So I think it's equivalent whether you write n equals k or n equals 1, but there's a couple options there for exactly how you express that. exactly one base case.
By the way, the trick here, Steve, I don't know if you saw it, was thinking about the two parts to the solution, where what are the number of factors when you use two and when you don't use two, right? And that was the recursion that you see in the last step there. So that's, again, almost all recursive things are about breaking the problem into subproblems. Yeah, and this one was a little bit different than some of the other ones I think that we, Hey, John, question. If a variable number of parameters, if you have a variable number of parameters, is there a way to refer to particular parameters, like refer specifically to the first one you pass in or the second one? I don't know how to do this in Scheme, but I know in Python, the answer is yes. It's just sort of in the order in which they are enumerated, the variable arguments with default values. I don't know how the star arg works in Scheme, Steve, John.
Yeah. In Scheme, you can write a procedure that gives you a scheme list. So let's just quickly go through the Python version, which is if you write star args. Args is not a particular name that you have to use. It's just a common one. If I want the third thing that's passed in, then I would just return args2. So then if I were to call f on 3, 4, 5, 6, 7, the third thing is 5, and that's what it would give me. And in Scheme, and by the way, this is not something that you're likely to see on an exam, but we did cover it in the course, so I guess it's possible, but I don't see it show up very much. You can define the same thing like this in Scheme. And what would it mean to find the third thing? Well, you have to treat args like a list and get the car of the cooter of the cooter of args. Hard to write Scheme right after you write Python. Okay, so then if you wrote F3, 4, 5, 6, 7, then you should get 5.
Okay, so the answer is it just treats it as a list. Yep.
Okay, so here we are in the spring 2020 final exam, question 4A. Complete the description of each function or method so that its behavior is described correctly. Okay, let's see what we have. We have a function called time, which creates a time value using data abstraction, and we can't see what it does. But there is a function format, which takes in a time and returns a string that formats this time, such as the hours, minutes, and seconds all have 2 digits. Okay, so however you build a time, we don't know, you can format it. And then there's this notion of a game. It's a class which has, as a class attribute, time. Every time you make a game, you take in a time, but you don't set an instance attribute. Instead, you set a class attribute. That means that the class attribute is going to get updated every time a game is made. And whenever you print out a game, what you see is the contents of the string format the self.time. Now, self.time in this case would refer to the class attribute. Why is that? There is no instance attribute called time because we never wrote self.time equals anything. And when you look up an attribute by name, you first look in the instance, it's not there, so then you look in the class. Okay, assume that time takes numbers and can represent hours, minutes, and seconds of a valid time and returns valid. That can be passed to format. Assume the format behaves as described, and a game instance is constructed from the return value of a call to time. Oh, so when you call game, you have to call it on time. So what happens when you print game time, game time? We're going to print. Okay, so these dot dot dots don't mean anything. This confused everybody when they were taking the exam. It was supposed to be just like this is a continuation of the sentence. The sentence is, this expression will display one of these 8 things. So we call game twice, which means this init method gets called twice, which means the class attribute game.time gets assigned twice. The first time will be to this 2:10, and the second time will be to 3 o'clock. when you assign the second time, that replaces the value that you assigned the first time. So now we've created these two games, and they're both instances of the game class, and the game class has a time set to 3 o'clock. Now it's time to call print. When you call print, you pass in these two objects. For each one, you invoke its stir method in order to format self.time. So we do format self.time for the first one, which gives us 3 o'clock. And we do self.time for the second one, which gives us 3 o'clock. You only see the contents of that string, so the quotes aren't there. And I think the answer is this second one. So this was really a question about order of operations. You have to create both games before you pass them into print. That's how call expressions work. Print is just yet another function. And so the stirring only happens after both the games were created. And when you create the second game, it overwrites the time for the first game.
For example, if instead of setting game.time in the class game, we said self.time, then the answer would be the first one, right? Because there would be two actual time instances. So the fact is there's only a class instance here. So that's why there's only one value of that counter.
People did not do terribly well on this question, if I recall. Yeah. It is interesting.
I think the little quote options are mean. I mean,
I think we gave like 3 out of 4 for those or something.
All right.
We gave a little.
I think it's mean. Like, what do I care if there's quotes printed or not?
It has officially been determined that I'm meaner than you are. So.
Yeah, that's right.
I don't think this will surprise anybody. It is interesting that if you were to print game of the first time, and then after that was all done, you were to print the game of the second time, you'd get a different answer.
Sure, of course.
And yeah, I mean, aside from my missing parentheses and the fact that, like, something would have to get returned here, it's like a little bit different. The basic story is that you have to figure out the order of which you assign game.time and you actually do the printing, which invokes the stir. Right. So this would actually give you the 210 and then the 3 in some kind of format. So let's see, what would Python display in this case, assuming we've started Python 3 and we've executed everything on the left. Oh, fun. So we've got some function called again, which defines again and returns again plus x. N is the sum of calling again z for z in range 9. Actually, we could work that out right now, and it looks like we have to in order to make progress. So let's do these first two before we even read the rest of this, because I think that will get us started. So what would happen if you printed the result of taking a list and appending 2? This is a question about the behavior of append. In this year's exam, you could just look it up. You should know it, though, which is that it alters this list, but it returns nothing. And when you embed that within a print, you're going to get the value of this expression, which is none, and that's what will be printed. So you really did add a 2 to a list that had 1 in it, but then that value was lost. It was never returned. It was never printed. Okay, now we have to figure out what this again function does, because we have to call it on every z from 0 through 8, not including 9. That's how ranges work. And I think that's going to take a lot of work to just draw the environment diagram. So maybe we should try to understand what it would do if you pass in some x. And it defines some function and calls that on x, and then adds x in. Now, it's important to note that this, again, has to refer to one of these two. Which one is it? It's the local one. So we made a new again, and that is what we're calling. So it's not like we're recursively calling again. It just kind of looks like we are, but since we use the again name, we're actually just calling this. And what does this do?
What kind of knucklehead defines 2 functions with the same name, John?
Well, I guess if the name's again, then it's okay. Okay. this one takes in x, which would be the same as y. It declares x non-local. It assigns this x, the non-local x, to be x minus y, where here x and y are the same thing. And so x is going to be 0. So not only have we, it's probably worth drawing out, not only have we returned 0, but we've actually changed x to be 0 because we subtracted x from it. So not only will this evaluate to 0, but by the time we get around to evaluating this, it will be 0 as well. So if we sum 0 for 0 through 8, then I'm pretty sure we'll get 0. Yeah, there are simpler ways to compute 0 than this. Okay.
That may be the best understatement of the semester, John.
So here we've got S is a list containing I for I in range 3. So this would be equivalent to writing out 0, 1, 2. This is S. Now we're going to append S. So what are we appending here? We're appending this whole list as a 4th element. Okay, and then this says for T in list S. Okay, so this is make a copy of S. So now we have all 4 elements, the 0 list, the 1 list, the 2 list, and the S list. And for each of those, we're going to extend it. A range from 3 to 5 is similar to a list containing 3 and 4. What extend does is it adds the numbers, the elements of whatever this is, into the list that you're extending. So we're going through each of these elements and we're putting 3 and 4 in it. And what's interesting is that this last element is the whole list S, so we need to put 3 and 4 into that as well.
Oh boy.
We can do it, we can do it. So that's what we built. Oh, and then it just asks us what's the length of this thing, which it has 1, 2, 3, 4, 5, 6 elements. And what is S1? That's a list containing 1, 3, and 4. Oh, we made it. Okay, we're getting close. This we're probably going to have to draw out. So if we have a class A whose class attribute B is 1, then it has an init method, an A method, and a repr method. And then we have B, which is a subclass of A, and it has its own class attribute B called 3. So these don't really relate to each other in any way yet. It is the case that any instance of A or B will have a lowercase b, but which one it is will depend on which class you are and whether it has any instance attributes called B, which some of them do, some of them don't. Okay. What happens when we create an instance of A where we pass in 4 as its A? Let's see what happens. Okay, so we're going to create this A instance. That's what happens every time you call the A class. In the local frame, you assign f equal to self.a. This is not part of the instance yet. This is just in the local frame. So I guess we should write that somewhere. We have init frame. It has an f, which is bound to the result of evaluating self.a. Well, at the moment, self.a doesn't find any instance attributes, so it will look in the class and find the A method. But this instance will already be built in. So this is like f is what you'd get if you took self.a and called it on something. I'll write it that way. It's a bound method. All right. Self.a, oh, and this has an a as well, of course. That's what we passed in. And that a was bound to 4 when we wrote the original call expression. So what happens when you write self.a equals a1 on? Well, a is the string for 1 onward, skips the first letter and gets our, and that's assigned to self.a. And what is self.a? That's an instance attribute of the a instance that we're creating. So this now has its own a, which is r. It also has its own b, which is 2. Now something interesting happens. F gets called on A. This is equivalent, based on what we've written, to having written, well, I guess it's not equivalent to anything because we changed A. But originally we were going to call this function, which self is the A instance and B is whatever we pass in. And we're passing in FOUR, the string. So what this is going to do is print out B is bound to FOUR and self. I'm not going to try to draw a lot of arrows, but I'm just going to write that A instance, this one. What happens when you print a list that contains B? Well, you'd see the 4. And you'd also print something else. The type of self is the A class, and it has a B, which is 1. So we're building a list. And what happens when you print a list? Well, let's just look at it really quick. If you print 4, you don't see the quotes. But if you print a list containing 4 and 2, then you do see the quotes. That's just like a quirk of lists. I don't think we graded that in this question, but that is true. So that's where these quotes are going to come from, is we're actually printing a list containing 4 and 1. Why 1? We did the following steps. We started here. We went to the class because we called type. We went to its B, which is 1. My gosh.
A follow-up request was to explain the line f equals self.a.
Sure. So whenever you have an instance of a class and you refer to a method in that class without calling it, what you create in this expression is called a bound method, which is a version of this method with self already filled in with whatever you had on the left of the dot when you evaluated this expression. On the left of the dot, in this case, is the A instance. I guess we didn't write this, but we should have. It's got a self, which is that A instance. This one. And so we're binding F to a function that would just take B with self already filled in. Now we call F. We haven't changed F along the way. We've changed self.a, but that doesn't matter. F is bound to this bound method, and F's not going to change unless you have another F equals line somewhere. And so we're going back and calling this bound method, which was this method with the self already filled in, and we called it on. So this does happen like occasionally in practice where, let's say you have 1, 2, 3. And you're like, oh, I'm going to have to append to it tons of times. Maybe you would say f is s.append. And then you can append to it a bunch of times. Just with this shorthand expression, and you see what s is now. We've appended to it 3 times. So that's a case where you might actually want to use this notion of referring to a bound method, and that's what f is. Whew, okay. what happened if we make a B 5? Well, when you create a B instance, I don't know where I'm going to put it. I guess I'll put it up here. There's no init here, so we're going to use the init here. We're going to bind f in the local frame to whatever I get when I look up a on a B instance, which finds this one. So f is now this function. This B instance gets its own a, which is I've, same process as before, gets its own b, which is 2. But when we get down to this line, we're calling this function instead. So we're calling this on whatever a is. A was 5 when we passed it in. I'll just put it here, make my life easier. So c is 5. What happens if we call a dot a on this b instance, and what I get when I look up b attribute on self? So it turns out it doesn't matter that I wrote this because we never refer to c again. But we do need to know what the b instance's b attribute is. It's the string 2. So this thing evaluates to 2. And what are we calling? A dot a is this guy. So we're going to print out that 2. And what we get when we look up the type of self is b, and look up its b, which is 3. Okay.
A student then pointed out that I never called the repr method.
Very good point. When you write this, then you have to do all the work to build it. That's why these things got printed out. You also need to display this value. And the way you display the value is to call the repr method, which I left out, but is very important. So in the first case, we should have written down the contents of the string self.a, which, where's our a instance? It was our. We would have had a separate line that looked like this. That's right. And b doesn't have its own repr method, so it does the same thing, except for self.a is different. So we get iv. Thanks. Okay, so this first line was from the print, and this is from the repr, which is what happens when you just display an instance of some class that has a repr method. Wow. What happens if we have f is lambda g h lambda p q, which takes all these things and calls them in a funny way? Well, this maybe is not so bad. So when you call f, you're filling in g and h. So we're filling g with a function that divides things in half, and h with a function that raises something to a power. But what it returns is a function that takes 2 more arguments. And here we get those arguments. So p is 3, q is 5. So this whole thing says raise whatever this is to the pth power, where p is 3. So we're going to cube something. And what are we going to cube? Well, we're going to cube half of q. And q is 5. This is floor division, so divides 5 by 2 and throws away the remainder, leaves you with 2. So this is 2, this is 3, this is pow. Raise 2 to the 3rd power gives you the number 8.